Greetings. Hello, welcome to another Math 104 lecture. So in the last lecture, we left off talking about polynomial long division. So we had done some examples, I had given some homework, and what we kind of established is that as long as you were dividing a polynomial where the higher degree was on top, you had a higher degree than you had a lower degree in the denominator, then you could, effectively use long division. And just to really reinforce this, your classwork assignment from the last lecture was x to the fourth minus 1 divided by x plus 1 times x minus 1. And you solved this classwork assignment last time by factoring. What I want to do today, just to get the ball rolling here, and just to finish up long division, is I want to take the same example and I want to show you that you can in fact do it by long division as well. So what we do is first let's figure out what the denominator is going to be. So in this case, we have x to the fourth minus 1 divided by, and now when we do the denominator here, what we're doing is we're just foiling, right? So this is going to be x squared minus 1. So x squared minus 1 is what we get because we see, oh yeah, we have a plus b times a minus b. This is difference of squares. We know that we should get a squared minus b squared. Okay, so we have x to the fourth minus 1 over x squared minus 1. And if we're doing this via long division, well, we know how we set this up. X to the fourth, and now we just have to fill in all the placeholders, right? So plus 0x cubed plus 0x squared plus 0x minus 1. Okay, and now what we do is we play the game that we always play, which is we figure out what we need to multiply by to the leading coefficient. And now at this point, I want to just stop and say, if you're okay with making sure that you're subtracting from the correct columns, then you do not need a placeholder in your divisor. But if you want, you can absolutely rewrite this. Instead of x squared minus 1, you can write it as x squared plus 0x minus 1, and that'll help you keep track of the columns that you're subtracting from, so that way you won't be making any mistakes. But as long as you are okay with subtracting from the correct columns, then you should be fine with just leaving it as x squared with minus 1. Okay, so we ask ourselves, okay, what do I need to multiply x squared by to give me x to the fourth? And in this case, well, we need to multiply by x squared. And by multiplying by x squared, what that does is we take our x squared and we multiply the entire divisor, x squared minus 1. So we get x to the fourth minus, and we put the minus x squared over here, right? Remember, we keep it in the x squared column because we're subtracting x squared. You can, once again, feel free to have that 0x as the placeholder. And if you had 0x there, 0x times x squared is the same thing as 0x cubed. So you would have, and I'm just going to write this in blue here just so we understand, you would have the 0x cubed term right here. But we see that 0x cubed plus or minus 0x cubed is not going to change anything, right? So that's why I'm just going to omit it here. Okay, so in doing so, what's going to happen? Well, we subtract everything, right? So x to the fourth minus x to the fourth gives me 0. That cancels out by design, right? We're always trying to cancel out the first term one at a time. So that cancels out. We're going to bring down that 0x cubed next. So 0x cubed comes down. And when that comes down, now we have the 0x squared, right? And 0x squared minus 1x squared, well, but it's minus a negative x squared. So this should become plus x squared, and then we have the 0x minus 1, right? So that entire piece has been untouched. Okay, well, now we ask ourselves, okay, do we have anything that we need to multiply by to get us 0x cubed? So this piece right here. And the answer is no. The reason that we don't have to worry about this is because there are no x cubes, and when we did our subtraction piece right here, notice that we didn't affect the x cubed column at all. So we can actually just leave this off. And the reason we can leave this off, once again, is because there are no x cubes that we need to deal with. If we had one x cubed or any form of x cubed in there, then yeah, we would have to worry about the coefficient. We would have to deal with, subtracting this off. because we're always trying to subtract off the leading term one at a time, right? We dealt with x to the fourth. Next up, we would have the x cubed that we would have to deal with, but because it's still just 0x cubed, even after our subtraction here, our first subtraction, we don't have to deal with it. So all we have right now is just this 0x squared, and then we can bring down the following pieces, right? So we have 0x squared plus 0x minus 1. But you ask yourself, okay, well, play the game here. This looks a lot like this. X squared plus 0x minus 1. And over here, our divisor is x squared plus 0x, technically, minus 1. And if you don't see it immediately, that's okay. You can just play the game like you normally do, and you ask yourself, what do I need to multiply by to give me x squared? Well, you already have an x squared, so just 1. So you know that you're going to have a positive 1 here. So positive 1 times x squared gives you an x squared, and then positive 1 times negative 1 is also still just a negative 1. So we have x squared here. We have 0 x's, right? We're not touching that column at all. And then we just have the minus 1. And then remember, we're just subtracting the whole thing here. And now when we subtract the whole thing, x squared minus x squared gives you 0. 0x minus nothing, right? We haven't done anything to the x column, and there are no x's, so that's just going to drop out as well. That's also just 0. And then you have negative 1 minus a negative 1, so negative 1 plus 1, which gives you 0. So we ended up with no remainder. And our final answer to this, to the division is x squared plus 1. And this should make sense because if you remember when we did the factoring, when we, factored x to the fourth minus 1, we ended up crossing some things out. We ended up getting an x squared minus 1 on both top and bottom. The x squared minus 1 on the bottom was just factored out into the x plus 1 and the x minus 1. Into these pieces because that's what we started with. So we factored the x squared minus 1 on top as well in the last lecture, and all those factors canceled out. All we ended up with left was x squared plus 1, which was irreducible. And we find that we end up with the same thing once again, x squared plus 1 with no remainder. So we have verified through 2 methods now that we end up with x squared plus 1 as our answer for this division. Okay, so that's the last thing that we're going to touch on for long division. I just wanted to do that again, that classwork assignment, just to reinforce that you can, in fact, do this by long division, and you can do it via factoring. Now, what we're going to move on to is called synthetic division. And what we just did, the example we just did, you cannot do via synthetic division. At least you can't do it via the method of synthetic division that we're going to be learning in this class. Technically, there is a form of synthetic division that you can use for powers higher than 1 when we're talking about x. But for the purpose of this class, you can only use synthetic division if your divisor is in the form x minus a. Okay? Don't get too hung up on the minus sign. Remember, what happens if a is negative? Well, if a is negative, then you have x minus a negative, which makes us x plus some number, right? So, you can have it in the form of x plus something as well. Just keep in mind that, the important piece here is that you have x and you have minus some number, right? And also the big factor here is it's x to the first power. If you have your divisor being x squared or anything higher than x to the first power, then you cannot use synthetic division. You cannot use the method that I'm about to teach you. You are forced to use factoring or long division. If you can factor it and reduce that way, try that. Otherwise, you have to use long division. Synthetic division will not work. Okay, so let's move on to synthetic division. Let's see an example of this. Okay, so let's say we had the following. Let's say we had 2x cubed and plus x squared minus 18x minus 7, and this is all being divided by x plus 3. Okay, so remember what I just said. Don't get too hung up on the fact that the x minus, because notice that we have an x plus something, but that's okay. And we'll see why it's okay in just a second. But x, as long as you have x plus or minus some number for your divisor and you're dividing some polynomial, you can use synthetic division. Because, again, notice that it's x to the first power. That's the important part here. Okay, so the way that we set up synthetic division is you take your number, whatever your number is. So in this case, our number is a positive 3. Okay, so we take whatever our number is in our divisor and we set that aside. We put it over here and we negate it. Okay, so instead of it being a positive 3, it's going to be a negative 3. Okay, and we put this in a box by itself way over here. Okay, so we have a negative 3 in a box. Now what we do with the piece that's being divided, the polynomial that's on top, is we only look at the coefficients, okay? Remember what coefficients are. Coefficients are the numbers in front of your variables. So the coefficient to x cubed is 2. The coefficient to x squared is 1, and so on and so forth. So we're only looking at our coefficients here. The reason that we do this, it'll, make a lot more sense when we get going, but coefficients actually will determine how the division plays out. A lot of people get the variables themselves. Believe it or not, the variables are not actually nearly as important as the coefficients are, and synthetic division really emphasizes this. So let's go ahead and list out our coefficients again in descending order. It's very important that when you're doing a synthetic division, you write it in descending order. Now, granted, it's already in descending order for us with x cubed first, but if x cubed weren't first, you would have to make sure that you write it first that way. Okay, so it's this in descending order. So we first write 2, 1, negative 18, and negative 7. Okay, so we are now getting started with synthetic division. This is now in the form that we can get going. Our process for synthetic division is you draw a line. Whatever your first coefficient is, just drops down immediately. You don't do anything to it. You get a 2 down here. Because we started with a 2, it's your first one, you get a 2. What you do now is you take this number and you multiply it against whatever your number in the box is. So we have a 2, you multiply 2 times negative 3, you get a negative 6, and you plug it into the next column, over to the right. So what I mean by that is you have a negative 6, you plug it in right over here. And what you do at this point is you add the numbers together. So you have a 1, you have a negative 6, you add them together, you get a negative 5. Okay, cool. So negative 5. And now you just repeat. So now you have negative 5 times negative 3, which should give you a 15, positive 15, right? Negatives cancel out. So you get positive 15. You write it in the next column over. You add the numbers together. So now you add the numbers in the column. Negative 18 and 15 should give you a negative 3. So negative 3. And then once again, negative 3 times negative 3 gives you a positive 9. So you have a positive 9 over here. And then negative 7 plus 9 gives you a 2. Okay, this number right here, I'm just going to box off real quick. The last number that you get, regardless if it's a 0, the last number that you get is always your remainder. Okay, so this number right here is your remainder. And what you would do is that tells you that this number is going to go over your original divisor, right? What was our original divisor? X plus 3. So you know that your 2 here is going to be the last thing that you write, and that's going to be 2 over x plus 3. And now we wrote this in descending order for a very good reason. The reason is now what we can do is we can go up from the remainder, reading from right to left, and that tells you what variable or what power of the variable that each of these numbers correlates to. So if this number on the far right is the variable, or I'm sorry, is the remainder, then the first number to its left, which I'm going to indicate in red over here, this number right here, is going to be your constant. This is just going to be negative 3. In blue over here, this is going to be, if the one to the right is going to be the constant, then this is going to be your x. So this is negative 5x. And then 2, this number right here, because again, you're going up in powers here, this is going to be your x squared. So when you write this all out, your final answer is 2x squared minus 5x minus 3 plus 2 over x plus 3. And we have solved this division. It's much, much, much shorter and much, much, much easier than long division. But the thing is that there just comes with the caveat that you can only use this method when you have x to the first power up here. And now how can you verify that this is actually, in fact, the answer? Well, just think about it. If we're only talking about our leading terms here. Notice how we have a 2x cubed here, and we're dividing it by something on the order of x to the first power. So this is essentially approximately equal to, well, this is 2x cubed over x. And what should you get here? Well, 2 over 1 should give you 2. X cubed over x should give you x squared. So we know that our first term here, this should approximately tend to 2x squared. And what did we end up with? Well, we ended up with a 2x squared with some other smaller terms to follow. So we know we're on the right scale. We're on the right order here. And then if you actually really wanted to show that this is in fact the correct answer, you can verify this with long division and make sure that your answer is correct. And as long as you get the same thing here as you got in long division, then of course you've gotten the correct answer. I'm not going to go through this verifying this with long division just with the interest of time here, but just keep in mind that that is a completely plausible way to check your answer. Okay, so we did an example in the last lecture video, and the example that we did was, let me write it out. It was 3x to the fifth, 3x to the fifth, and we're going to add to it 5x to the fourth, and we had plus x plus 5. And this is all being divided by x plus 2. Okay, so x plus 2. And now what I want to do is I want to do the same thing. In the last time that we did this example, we did it via long division. I want to do the same example now with synthetic division. Okay, so how do we set this up? We set this up the same way, right? So we set this up the same way that we just did the last example, where we first look at our denominator. We see what our number is. Our number is a positive 2, so we negate it and throw it in a box. So instead of it being a positive 2, we know that it's going to be a negative 2 in the box. Then we look at the coefficients for each of our numbers and we start listing them out. Now, granted, they're already in descending order, so you don't need to do any, moving around. But if they weren't in descending order, you would have to put it in descending order. So we write, okay, we have a 3, we have a 5, and now you stop and you say, wait a second, what did we do for long division? When we were writing this in long division, with, the x plus 2 over here, and we had 3x to the fifth, and we had the plus x to the fourth. What we had to do was we had to put placeholders, right? We had to put a placeholder for the 0x x cubed and the 0x squared, right? You have to do the same thing for synthetic division, except we only care about the coefficients, so you just need to write zeros. So we have a 3, we have a 5, we then write a 0 for the x cubed, we write another 0 for the x squared, and then we can continue along, right? We have a coefficient for x, that's going to be 1, and we have the 5, which is just our constant, so we write that there. Okay, we draw our line. We know our first term always drops down. No matter what, first term drops down. We take our first term, we multiply it against our number in the box, so 3 times negative 2 gives me a negative 6. And now we continue with our addition, right? We add, then we multiply, then we add, then we multiply, and you just keep doing that until you're done. So we add here 5 times negative 6, I'm sorry, 5 plus negative 6, my mistake, gives you a negative 1. Negative 1 times negative 2. That it gives you a positive 2, which you throw in the next column over, right? So positive 2 over here. You add them up. 0 and 2 gives you a positive 2. 2 times negative 2 gives you a negative 4. You throw this in the next column, and you add the column. 0 plus a negative 4. Well, that's 0 minus 4, so negative 4. And negative 4 times a negative 2 gives you a positive 8. Okay, 1 plus 8 gives you 9. 9 times negative 2 gives you a negative 18. So negative 18, and when this is all said and done, you add the last column, you get a negative 13 over here. And now remember, your last number right over here, which I'm going to draw dotted lines just to separate it, your last number is always your remainder, right? Negative 13 is always your remainder. So what does this tell you? This tells you that every number moving forward starts with the constant, then the x squared, so on and so forth, right? So when we write this all out, we know that our final answer is going to be, well, if this is our constant, this is our x squared, this is our x to cubed, and this is our x to the fourth. Well, we write 3x to the fourth minus x cubed plus 2x squared minus 4x plus 9, and now we have this remainder, so we have minus 13 over our original divisor, which was x plus 2. And this should, in theory, be the same exact answer that we got from the last lecture. And looking at my notes, this is the same answer. So we've now verified that we got the same thing in synthetic division that we got in long division. This here is your final answer, okay? The hardest part of this, by far, the hardest part of this is two things. One, remembering your setup. And what I mean by setup is remembering that in the box here, you are negating whatever number you have here. If you have a positive 2, it needs to be a negative 2 when you put it into the box. Okay. And then the second thing that I know a lot of students trip up on is you can do the whole synthetic division and you get all your numbers out and then you just list it incorrectly in your final answer, okay? Just go in descending order, right? And then start from right to left when you're reading this. If you know, and I'm gonna draw this in a red arrow again, if you know that this here is your remainder, the next number over has to be your constant. The next number to the left of that has to be your x, then your x squared, then x to the third, so on and so forth, right? So if it helps you, feel free to draw little arrows like mine and just, make it make sense to you, right? So you could just say that I'm going to put a c here because this is a constant. This is going to be my x squared, my x cubed, my x to the fourth, and then just write everything all out like I just did here. And this is going to be your final answer. Okay. And now, once again, how do you verify that this makes sense in your head at least? Well, when we're dividing, we were dividing 3x to the fifth. Right? And when we're talking about our leading terms here, we're talking about 3x to the fifth being divided by essentially x, right? So this is approximately, we know that our leading term is going to tend to this piece right here, which is 3x to the fifth over x, which when we know is going to give us 3x to the fourth. And what is our first piece? 3x to the fourth. Okay, so we know that we're in the right ballpark when we do this because of our little test here with our leading terms and what, polynomials tend to. And we talked about, how polynomials tend in a couple lectures ago. So, feel free to remind yourself with that definition if you're unsure of what I'm talking about when I say a polynomial tends to something. Okay. Okay, so now you guys should be ready to do your first classwork assignment. So I'm going to go ahead and clear this off. So go ahead and give your first classwork assignment a shot. It's 3x cubed plus 2x minus 11. And this is all being divided by x minus 3. And I want you to solve this, using synthetic division. Okay, so give it a crack, see what you come up with. Okay, so doing this together, how do we set this up? Your first piece is you look at your divisor, your x minus 3 here. You take that number, that, the constant that's next to your x, and you flip the sign. So instead of it being a negative 3, well, it's just going to be a positive 3 in a box. So we have a positive 3 in a box. Great. Now we take our coefficients to the piece that's being divided, the polynomial on top. So we have a 3. But wait, we have a 3x cubed, but do we have an x squared? No, right? So you need to make sure you put the 0 in there as your placeholder for your x squareds. So you have 3, 0, then you continue along and you have 2 and minus 11. Okay, you draw your line. You know that your first term is always going to come down. That's going to be a 3. And now you go ahead. You multiply, you add. You multiply, you add. You continue until you're done, right? So 3 times 3 gives you a 9. You throw that in the next column, you add, you get a 9. 9 times 3 gives you a 27. So 27 comes over here. 2 plus 27 gives you 29. Okay, well, this can get a little annoying, as the numbers get larger sometimes, but that's okay. 3 times 29, the way I do this in my head is I do 3 times 30, which is 90, and then I subtract off 3, right? So instead of it being 90, it should be 87. So we have 87 over here, and if that didn't make sense to you, that's okay. Just feel free to use a calculator for this if you need to, or practice your multiplication skills, whatever the case may be. So you have 87, and now you add these pieces together, negative 11 and 87. Well, it's the same thing as 87 minus 11, so that should give you 76, right? 80 minus 10 should give you 70, and then 7 minus 1, 76. Okay, so what does this tell you? This tells you, once again, that 76 is your remainder, right? Then this piece right here is going to be your constant. This is your x, and this is your x squared. And does this make sense? Yes, right? If you're dividing something that's cubic, 3x cubed, and you're dividing it by something that has a highest power of 1, x to the first power, you know that by default you're going to be in the ballpark of x squared, right? This is, 3x cubed over x gives you something, with whatever coefficient, in this case it's 3, but it gives you something in the realm of something squared, right? X squared. So we know our highest power is going to be x squared. And so when we write this, we have 3x squared plus 9x plus 29 plus 76 over our original divisor, which was x minus 3, and we're done. Okay, feel free to verify this via long division if this doesn't make sense to you, but this should fall out and you should still get the same answer regardless if you use synthetic division or long division. Okay, so that's synthetic division in a nutshell. It's, for most students, that tends to be the easier approach for dividing polynomials. But again, just make sure that if you're going to use it, your divisor is x to the first power and then some number, right? Whatever the number is, you just negate it when you set up your synthetic division. You flip the sign of it, right? And the reason that we flip the sign, if you were wondering, is because if we have some polynomial f of x, the reason that we're flipping the sign is because synthetic division is defined as some polynomial being divided by x minus a. Now, remember how I said don't necessarily worry too much about this minus because, it could be a plus and you'd still follow the same pattern. Well, that minus here is built into the definition of synthetic division. So basically, if you have x minus 3, it's not a negative 3, it's x minus the positive 3, which is why when you flip the sign and you set this up, you would just have a positive 3 in the box. Okay, but if you don't understand that, that's totally fine. Just understand your process, which is you take whatever the number is on your divisor, you flip it when you put it into the box, and then you start your process with synthetic division. Okay, so let's move on here. There are not that much left in this chapter. The last two things left in this chapter that we need to talk about are two theorems, okay? So one of them is called the remainder theorem, and one of them is called the factor theorem. And the factor theorem is actually kind of a special case of the remainder theorem, but it tells you a great deal of things. Okay, so the remainder theorem. Let me go ahead and write this. So give me 1 second. Okay, I'm going to abbreviate theorem here. So remainder theorem. If you have some polynomial, and for this case, I'm just going to call it f of x. Okay, so if you have some sort of polynomial f of x, and it's being divided by x minus a. Now remember, this x minus a, this comes up a lot, right? That was the thing that we just had in our synthetic division, x to the first power minus some number or plus some number, right? So if you have some polynomial being divided by x minus a, then and I'm going to abbreviate this piece right here, the remainder of of this division is always going to be r is equal to f of a. Okay, let's break this down what this means here. So you have some sort of polynomial up top, right? So f of x. And what do I mean by some sort of polynomial? Remember, polynomials are always in the form of, descending order. You could have, just for a quick example, you could have like x cubed plus 7x squared minus 4x, yada, 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 right? And so the entire idea is you have some sort of polynomial up top, and you're dividing by something in the form of x minus a, okay? Now, the remainder theorem doesn't tell you the full answer. It's not going to tell you what the division comes out to be, but what the remainder theorem tells you is it'll tell you exactly what the remainder comes out to be. So in our last example, we had a remainder of 76 over, what was it, x plus something, sorry, x minus 3. Our remainder was 76 over x minus 3, right? So what the remainder theorem tells you is that it can tell you your remainder before you even do that division. Okay, so the way that you do this is now notice a is your input to the function, right? So what it's telling you is that if you take this number right here and you plug it into the function that's on top, your remainder will be whatever your output is when you plugged in a into your function. Okay, this makes a lot more sense when we start, going. So let me go ahead and give an example. So we actually just did this division. So the division that we just did was 2x cubed plus x squared minus 18x minus 7, and this was all over x plus 3. We just did this one not too long ago. Okay, so if I said I want you to find the remainder of this, well, the way that you set this up is you say, okay, well, my remainder is equal to my function at -3. Remember, this negative sign is built in, right? So if the negative sign is built in and you have an x plus something, this is really the same thing as x minus a -3. And so a is whatever number and sign follows that negative. So because we started with an x plus 3, we converted it to the form of x minus something, so x minus a -3, which we know is equivalent. And now we just take this -3 piece, and that is what we're going to be plugging into the function on top. So the function on top, what happens? Well, you're taking -3 and you're plugging it in everywhere that there's an x, right? This is now your input to your function on top, or to your polynomial on top. So this is the same thing as 2 times -3 cubed plus -3 squared minus 18 times -3 minus 7, right? Wherever there was an x on top in your, in the numerator, now I'm plugging -3 in. And what happens here? Well, when we simplify, let's just go ahead and do some simplifications here. We have -3 cubed is going to give us, well, that should give us a 27, right? -27. So we have 2 times -27. So 2 times -27. Then over here, we have a +9. The negatives are going to drop out, right? -3 times -3 is a +9. Over here, we have -18 times a -3, which should give us a positive number. So we have a positive, and let's figure this out. Again, my process, pretty similar to how I did it before. I would multiply 3 times 20, and 3 times 20 gives me 60, and then I subtract 6 off. So now I get 54. So I have positive 54 and -7. Again, if you don't understand how I got positive 54 here, just plug into your calculator -18 times -3. You'll get the same thing. Okay, 2 times -27, well, that is -54 plus 9 plus positive 54 minus 7. And these pieces cancel out. We just have 9 minus 7, which gives me a 2. And if you remember from the last time we did this example, which was our first synthetic division example, we had a remainder of 2 over x plus 3. Notice we ended up with the same remainder, 2. And this, when you do this, if you were to actually do the division, what this tells you is that you would take this 2 and throw it over x plus 3. So we got the same exact remainder just by following the remainder theorem. Okay, so again, just to explain the process one more time, the process here for the remainder theorem is you take your remainder by plugging in whatever your number is. So in this case, your divisor was a -3 because we needed to change the form from it being an x plus 3, right? We started with it being x plus 3. We changed it to be x minus a -3. So we know that we're taking -3 and plugging that into our top polynomial. And then when you plug it in, you just do your simplifications. You get some sort of output. In this case, you get a 2, and that's your remainder as if you were to do the entire division. Okay, so you can fact check this. You can double check that this is in fact the case by doing some sort of division, whether it was synthetic division, long division, whatever the case may be. And we already did it before, so I'm not going to do it again because this was one of our first examples for synthetic division. But the point is that you can do that entire division. You'll end up with some sort of remainder, and that remainder will match whatever you get from the remainder theorem. Okay, so we got a remainder of 2, and that would be your answer. Okay. Let's do one more example on what I want you guys to do. This is your classwork assignment. So I want you guys to use the remainder theorem on the classwork assignment from before. So the one that we just did, which was 3x cubed plus 2x minus 11 over x minus 3. I want you to use the remainder theorem of this and tell me what the remainder is going to come out to be by using the remainder theorem. Okay, so give you guys a couple seconds and hopefully you guys can figure this one out. Okay, so again, the way that you set it up, well, you already have an x minus a number, right? So you don't need to do any sort of manipulation in the bottom. So because it's x minus a number, we are going to take whatever the number is that follows that minus. Again, the minus is already built into the remainder theorem, just like the minus is already built into the synthetic division. So what we do is, okay, your remainder is going to be your top polynomial, so we call it f of whatever, at that particular number. So in this case, at 3. Okay, so what that tells you is that you're going to plug in 3 wherever there's an x on top. So we have 3 times 3 cubed, instead of it being x cubed, plus 2 times 3 minus 11. Okay, so doing some simplifications, 3 cubed is 27. So we have 3 times 27 plus 6 minus 11. Okay, 3 times 27, this is the same thing as 3 times 30 minus 9. So 3 times 30 is going to be 90 minus 9 gives you 81. So you have 81 minus 11 plus 6. I just moved the minus 11 closer because I see that I have, something in the ones place here. So I can, subtract that off. So 81 minus 11 should just give you 70. And then 70 plus 6 gives you 76. And notice that from the last classwork assignment, you ended up with a remainder of 76 over x minus 3. Well, your remainder matches 76. That is your exact remainder that you got before from doing the classwork assignment. And you have now showed that you would get the same remainder by the remainder theorem. Okay, so hopefully this isn't too bad. I'm not going to do another example of this. If you guys do want more help with this, please feel free to reach out. I'll be happy to go over more examples with you, on a case-by-case basis. Okay, so with that being said, let's move on to the factor theorem. Okay, factor theorem is, again, a special case of the remainder theorem. The reason is that what we're caring about is if we get a remainder specifically of 0, okay? And now what did I tell you guys before? When we were doing our long division or our synthetic division or, factoring, whatever the case may be, if you got no remainder, then your divisor is going to be a factor, okay? If you got a 0 for a remainder, then you have the whatever you were dividing by was a factor of the polynomial on top. So let's write this off in actual math terms. So factor theorem. Okay, so factor theorem says if you have polynomial f of x and it's going to have x minus a as a factor, and you might not have seen this before, IFF. I'll go over it in just a second. And then the following, f of a is equal to 0. So how this reads is polynomial f of x has x minus a as a factor if and only if, so if and only if your polynomial at a is equal to 0. If and only if, what does that tell you? That tells you that you can go in either direction. They imply each other, okay? So if you get this piece first, you can go backwards and say, okay, yep, polynomial has x minus a as a factor. And you can go in the opposite direction and say, okay, well, if polynomial f of x has x minus a as a factor, then my remainder should be 0. Okay, so if and only if means you can go and you can take the sentence and each piece implies the other piece. Okay, so this is a very strong theorem because it, regardless what piece of information I give you, so if I give you the fact that your remainder is 0, then you know that x minus a is a factor of f of x. And if you go in the other way, if I tell you that x minus a is a factor of f of x, then you know that the remainder is 0. Okay, so whatever piece I give you implies the other piece. That's the power of if and only if. Okay. If you've never seen that before, that's okay. If and only if pops up occasionally in lower math classes, and then you'll see it more and more and more in higher math classes. So hopefully that's a very, very, very brief introduction to it if you've never seen it before. Okay, So what I want to do is let's do an example here. I want to find all the solutions to the following equation, given that a solution is -2. So let's say we have 3x cubed. Oops, I ran out of room at the bottom here. Give me 1 second. Okay, so let's say we have 3x cubed minus x squared minus 20x minus 12 is equal to 0. And now what I want to do is I want to find all the solutions to this polynomial here, given that I already know one of the solutions is -2. Okay, so given x is equal to -2 is a solution. Okay, so how are we going to approach this? Well, if I know that -2 is a solution, then what that tells me is that -2 is a factor of the above piece, right? So that means that x plus 2 right here is a factor of the above polynomial. And again, I know that just by moving that plus 2 over, right? So this is the same thing, x plus 2 is equal to 0, and we know that we would have solved for x at this point by, moving the 2 over, and that's how we got x is equal to -2. So we're kind of moving backwards, right? We were given that x is equal to -2 is a solution here, and we want to find all the other solutions with this one piece of information. Okay, so what we can do here is we can take our solution, which is x is equal to -2, and I'm going to use that for my synthetic division. And the reason I'm going to use that for my synthetic division is that I know I shouldn't get a remainder back because x is equal to -2 is a factor. So by factor theorem, x plus 2 should be a factor of this whole piece. Okay, so let's set this up here. We know we're going to have -2 in a box. And if you're wondering why it's -2 when we were given x is equal to -2, it's because, again, the original factor was x plus 2, and this was equal to 0, right? So you would have flipped the sign, but in this case, we've already solved for it, so we know that it's -2. Okay, so we have -2 in the box, and now what we're going to do is we're going to write our, each piece in descending order, only talking about the coefficients here, right? Just more synthetic division practice. So we have 3, -1, -20, and -12. Okay, and just double checking. Yes, okay, perfect. Okay, so what we're going to do is we're going to draw the line. We're going to pull our first piece down. So that's a 3 pulling down. And now we just go through the way that we normally go through, right? So 3 times -2 is -6. We add, get -7. -7 times -2 is a positive 14. We add, we get -6. -6 times -2 gives me a positive 12. And when we add, we get a 0. And we should expect to get a 0 by factor theorem, right? We were told that x plus 2 is a solution. So by factor theorem, that tells us that when we plug in -2, that we should get a remainder of 0. F at -2 gives me a remainder of 0. Okay, and now we could start to see how factor theorem actually is just a subset of remainder theorem. It's just a special case of it. Okay, so now, okay, our goal here again is to figure out all the solutions to the polynomial. So what did we do by doing this? Well, what we found out is now we have a remainder of 0. We have a constant of -6. We have -7x, and this is 3x squared. So what this tells us is that this piece right here can be broken up into the following. We can take our equation here, and I'm just going to erase the information that we were given. Sorry, I'm running out of room here. What we can do is we can rewrite this as our first given solution, which was the factor of x plus 2, times everything else that we just figured out. So what we just figured out is when we take out x plus 2 from the larger polynomial, we're left with this piece left over. So we're left with 3x squared minus 7x minus 6. Is that right? -7x minus 6? Perfect. Okay, is equal to 0. So what we did is essentially we factored this. We factored out the x plus 2, and we found what would be left over when we factor out x plus 2. Okay, so what we're going to do now is, well, we're just going to keep factoring. So let's go ahead and keep factoring, and we're just going to factor this piece now in the middle, and factoring that piece in the middle. And again, I'm just going to get rid of this for the sake of room here. So how do we factor that? Well, we're just going to keep the x plus 2 on the outside, but on the inside, you do a times c, right? Going way, way, way back to what we first learned, a times c. So 3 times negative 6 gives you a negative 18, and we need to think about, two numbers that would add together to give you a negative 7 and multiply to give you a negative 18. In this case, it's going to be negative 9 and positive 2, right? So we have 3x squared minus 9x plus 2x minus 6 is equal to 0. Okay, going through this, again, we keep the x plus 2 on the outside. For this piece, I am going to group them together. So I'm going to group them with that and then with those. So grouping for the first set of parentheses, that means I'm going to pull out the largest piece that I can. So I'm going to be pulling out a 3x. So we have a 3x here times, and we have x minus 3 left over. And over here, I'm going to pull out the largest piece I can, which is a 2. And we have x minus 3 left over again, which is equal to 0. Okay, and last but not least, you do the distributive property, but just now in reverse, right? So we continue to bring down that x plus 2. Our first piece that we're taking out is the x minus 3, so we're taking out an x minus 3 from both terms. And last but not least, we have everything left over, so the 3x plus 2, this is all equal to 0. And now this is entirely factored. So what did the factor theorem allow us to do? Factor theorem allowed us to get 3 different factors for this cubic that we started with. We started with 3x cubed minus x squared, yada, yada, yada. Beforehand, we really don't have a way of, solving this. We didn't have a way of dealing with this without factor theorem and synthetic division or long division. You could have also used long division. But point is, we didn't have a way to do this without factor theorem and polynomial division. But now, with both of those in mind, we were able to get this x plus 2 on the outside. We were able to also break down this quadratic. And breaking down the quadratic, we got 3 separate factors here at the bottom. And we all know how to do the rest here. So doing the rest, we would set each piece equal to 0. We've already done this piece here because that was given to us, the x plus 2. We know that negative x is equal to negative 2 is a solution. Again, that was given information. So we're just going to do the other ones. So doing the other ones, that means we're going to have x minus 3 is equal to 0. And 3x plus 2 is equal to 0. And when we solve this, we have x is equal to 3 and x is equal to negative 2/3. So all of the solutions, which is the original goal here, all of the solutions are negative 2, which we were given, negative 2/3, and 3. And we're done. Okay, so again, breaking this down, we were given this polynomial here. And we were also given the fact that x is equal to negative 2 is a solution. So what we did was we tried to factor out the x plus 2, because again, we know that x minus 2 is the same thing as x plus 2 is equal to 0. So we know x plus 2 is the real factor here. So what we did was we tried to break out this x plus 2 here. And the way that we did it was by synthetic division. And the reason we know we could do that is by factor theorem, because if x plus 2 is a factor, then we know we should get a remainder of 0 when we do synthetic division. If we didn't know this, if x is equal to negative 2 was not necessarily a solution, then factor theorem would tell us, oh, well, we don't actually know if we would get a 0 here when we do synthetic division, and then we could possibly end up with a remainder. And if we ended up with a remainder, then we've actually shown that x plus 2 is not a solution. But in this case, because it was given information to us, we know that it is in fact a solution, so we know that the remainder should equal 0 when we do, some sort of input. And as a result, we know then that we could break this up into x plus 2 and whatever the output is from our division of taking out x plus 2. So we use synthetic division to find the quadratic, and then the rest of this is pretty boilerplate, right? The rest of this is stuff that we already know how to do going way back. We just use our a times c method, break this up, do our grouping, and we end up with our 3 solutions, which one of them was given to us. Okay, so hopefully that's not too bad, but we'll do another example, and this is a more direct example of using factor theorem. This one here was a little more abstract because we were just kind of using the definition of factor theorem, but in this example, and this is the last example that we're going to do here today, this is going to actually show how to use factor theorem. Okay, so here's the question here. I want to show x minus 1, that's a minus, sorry, x minus 1. So show x minus 1 is a factor of 2x cubed plus 3x squared minus 6x plus 1 using, and I'm going to abbreviate this as factor theorem. Okay, so using FT. And then what I want you to do is I want you to also check this with synthetic division. Okay, so your last classwork assignment is going to be the check, but we'll go through that together. Okay, so here again, just restating this, we want to show that x minus 1 is a factor of this polynomial that we have here using factor theorem. Okay, so what do we know? We know that if, by factor theorem, if the remainder is 0 when we plug in our a, and in this case, a is positive 1, right? A is whatever comes after the negative sign. So if we plug in 1 into our polynomial and we get a 0 back, then x minus a is a factor. Okay, so the way that we set this up is, well, we'd say f of 1, right? Again, the 1 is coming from that x minus piece. So f of 1 is equal to 2 times, and wherever there's an x, we're plugging in 1, right? So 2 times 1 cubed plus 3, 1 squared minus 6 times 1 plus 1. Okay, and now doing this, we're just going to go ahead and start simplifying. 1 cubed and 1 squared all drop out to just be 1. So you have 2 times 1, which is 2, plus 3 times 1, which is 3, minus 6 plus 1. 2 times 3 is, or I'm sorry, wow, 2 plus 3 is 5, minus 6 is negative 1, plus 1 gives you 0. So we get 0. So yes, by factor theorem, x minus a, or in this case, x minus 1, is in fact a factor of this polynomial right here. So we have shown that. Okay, again, we have shown it just by getting a 0 as your output. And this is it. That's all you need to do. You just need to plug in whatever your a is into your factor. And now remember, I'm sorry, into your polynomial function. And now recall that this is very, very similar to the remainder theorem, right? What are you doing in the remainder theorem? Well, in the remainder theorem, you're taking whatever comes after your negative sign and you're plugging it into your polynomial, and then whatever you get back out is your remainder. It's just that in this case, the remainder is 0. So by factor theorem, because you got a 0 back for your remainder, you've shown that x minus 1 is a factor. Okay, so factor theorem and remainder theorem go very, very, very closely together. The only difference is that in factor theorem, it specifically states that if your remainder is a 0, then you have a factor. And that's just it. Okay, so now I want you guys to do your last classwork, which is the check. So doing the check, that just means do this via synthetic division and make sure that you get a 0 for a remainder using synthetic division. Okay, so I'll give you guys a couple seconds just to see, and just I'll pull up my screen here. Again, it's this polynomial being divided by the x minus 1 piece, right? So and I'm just going to get rid of this, x minus 1. Okay, so what we have to do, again, we put our number in a box, right? We already have x minus a number, so whatever that number is just goes in the box. So it's going to be a positive 1 in the box, right? Okay, so positive 1's in the box. Now we just take our coefficients here. So our coefficients are going to be 2, 3, negative 6, and 1. We know we're dropping down the first one. We put our line down here. We drop down the first coefficient. That's just a 2. We do our first multiplication. 2 times 1 gives us a 2, and we add, so we get a 5. 5 times 1 gives me a positive 5. Plug this over here. When we add them, we get a negative 1, and negative 1 times a positive 1 is a negative 1. And when we add these, 1 and negative 1 give us 0. And yes, right here, notice we get a 0 for a remainder. So our synthetic division check worked out. We got a 0 for a remainder, just like we got a 0 for by factor theorem. So yes, x minus 1 is in fact a factor of 2x cubed plus 3x squared minus 6x plus 1. And to go a little bit further, what you would have left, what you'd have left over is you'd have 2x squared plus 5x minus 1 as your, the polynomial that's left over. But this piece right here that I just circled, that wasn't part of the question, just more practice for you to derive. This is your constant, this is your x, this is your x squared, right? Because it's, ascending from the remainder. All right, guys, so that's it on chapter 3.3. Again, we covered a lot here. We covered division by factoring, division by long division. Then we covered synthetic division, and then the two big theorems, remainder theorem and factor theorem. Okay, I'm going to be posting your homework, so give this a shot, see what you come up with. And if you have any questions at all, please feel free to reach out to me, and I will try to help you out as best as I can. All right, guys, enjoy the rest of your day, night, morning, whenever you're watching this, and I will talk to you later. Have a good one.